the Newton's second law lab, and most of this we did in class, but we'll just go over this for you real quick. Don't forget that each car weighs 500 grams, and 500 grams is the same thing, divide that by 1,000, 1 kilogram, as a half of a kilogram. And the weight on the hanger that you added every time was 50 grams, and that ends up being 0.05 kilograms. And so if you are doing the side where you're changing the force on the hanger, you only had one car. So this first column here would be 0.5 kilograms for the one car, plus the 0.05 kilograms for the weight. And so that originally would be 0.55 kilograms. And then each time you added 50 grams to the weight hanger, so this in the second column we had 100 grams total, so that'd be 0.6 and then 0.65 and so forth on down. The distance of the card is always 0.75 meters. Try this again, I'm sorry, I made a big mistake there, 0.075 meters, because that's 75, just keep making this mistake over and over again, 7.5 centimeters. You divide that by 100, because there's 100 centimeters a meter, that gives you 0.075 meters on each one of these all the way down. Okay, so like that all the way down, even on the other side. The time in seconds, you're going to use the gate time on your computer. Do not use the column that says just time. Make sure you're using the gate time, because the card is going to the gate. On this acceleration right here, you're going to use 2 times the distance. Well, that distance is the distance of the card, so it's going to be 0.075 each time, and then you're going to divide that by the gate time. So let's say the gate time was, I don't know, 0.1 seconds. I just made that up. You'd put 0.1 and square just the time. Don't square the whole thing. It's 2 times the distance of the card divided by the time squared. The mass on the hanger, since you're on the force side, once again, you're changing that hanger's mass by 50 grams or 0.05 kilograms each time. So that'd be 0.05, then 0.10, and 0.15, and so on. And on the force on the hanger side, since it's the force on the hanger, you got to use the mass of the hanger. So you're going to show the formula each time. I'm going to take the mass of the hanger, which is 0.05, multiply that by 9.8 meters per second squared, and you will end up getting 0.49 newtons in that first box. Then in the second box, naturally, you doubled it. You're going to show that formula every time. I got such a big marker, I can't fit it all in one box up here. But you show that whole formula each time. So in the second box down, it would be 0.1 times 9.8, and you get 0.98 newtons and so forth. Now, if you flip the paper over, now you got this chart, and the only difference in this chart is the fact that this one says the relationship of mass to acceleration. So now you're changing the number of cars. So I started off with 1 car, and then 2 cars, and then 3 cars. Well, the same thing that was over here, you had 1 car of 0.5 and 1 weight hanger of 0.05. You're going to have that same mass right here of 0.55 kilograms. But in the second box down, you had 2 cars. Well, 2 times a weight of or mass of 0.5 kilograms, that gives you 1. But you also had to add the 0.05 for the kilograms for the weight of the hanger. So this would be 1.05 kilograms, and then 1.55, and so forth on down. The distance of the card is always 0.075, like we did on the other side. The time in seconds is gotten from the gate time. Make sure you use the gate time. The acceleration, once again, is going to be 2 times the distance of the card. So it's going to be 2 times 0.075 divided by the square of whatever that gate time was. The mass on the hanger will always be 0.05 on this side. It never, ever changes, because what you're changing is the mass of the cars. You're adding more cars, not adding more force. And so therefore, this number right here under force will always be the same, because you're always doing force equals mass times gravity. So you're always doing 0.5 times 9.8, and that gives you 0.49 newtons each block. So every block is going to be the same for that particular thing. On the next page, this is one where you really got to pay attention here. I said use the graph paper to draw the mass times acceleration graph and the force times acceleration graph. So the graph paper looks like this. I want you to look at my scales and copy those scales on your paper. So this one here is the force or an acceleration graph. I have acceleration on the y-axis, force on the x. And if you notice on the force axis, or on the x-axis, I went up by 0.2s each time. So every line is 0.2. Make sure, I don't know why I said 0.2. Every line is 0.1 each time. So it's 0.1, 0.2, 0.3, 0.4. Keep doing that, and it's all done in newtons. On the acceleration side, since you have some pretty drastic accelerations with the weight you're putting on, I went up by 5. So every line was 5, 10, 15, 20. So I do that on your paper as well. On the next chart, this is going to be the acceleration over mass chart. Once again, on the bottom, I went up by 0.1s, so 0.1, 0.2, 0.3. But if you notice to spread the graph out a little bit, on the y-axis on this side, I went, every other line is 1. So let's start off with the 0 down here. And then I went 1, and then skipped a line, went 2, skipped a line, went 3, skipped a line, went 4, and so forth. So that'll spread your graph out a little bit if you do that. So please copy my axis on your graph paper. And then lastly but not least, I want to show you something that can be misinterpreted on the directions. It says in number 11 to place the data in L1 and L2 of your calculator. Hopefully you remember how to do that by hitting the Stat button, and then you hit the Edit button, and that will allow you to put stuff in L1 and L2. So L1 is going to be your x-axis, and L2 is going to be your y-axis. So whichever graph you're doing, you do that. Then it says write a regression line equation. Well, that's where a lot of people get confused because it's not necessarily a line. If you have a acceleration and force graph, it's going to look almost like a straight line like that. So that would give you a regression line. But on the other graph, it was a acceleration over mass graph. And this one here looked a lot different. It gave you a exponential equation, something like that. So please, please, please don't use a linear regression line for each one of those. On the mass over one, you're going to want to use the exponential equation, which I think is y equals abx. So x is your exponent of b there. So make sure you're using that one. Or you can simply use a quadratic equation of ax squared plus bx and so forth. So whichever one you want to use, but don't use the linear regression line. Then it says, once again, write a regression line equation. It's not always going to be a line equation. Make sure you're using this here for that as well. Now this thing called the R value. If your calculator is not saying an R equals, I want you to go into the catalog. Let me rewrite that. There's a catalog button on your TI-84. And underneath catalog, you're going to go down to diagnostics and turn the diagnostics on. And when you do that, you come back up here and do these equations, it'll say something that R equals like 0.98. Well, the closer that number is to 1, the more the data fits the equation. So if your data is a little bit off, it'll be like 0.8. But if it's almost right on, it'll be 0.99. If it's dead on, it'll be 1. So you're really hoping that we get an R value close to 1. If you do get an R value close to 1, that means you just proved Newton's second law because all your data is matching your formulas. And the very, very last thing says, how does this information confirm or prove Newton's second law? Well, you got to remember what Newton's second law says. That is, force goes up, your acceleration goes up, and it's directly proportional. And so if you're matching your equations, I don't know why I said direction, I meant directly proportional. And if mass goes up, then acceleration goes down because it's inversely proportional. And that's where you get the curved line. So that's what you're trying to prove by doing all this. So proportional, I just spelled that really bad. I'm glad this is on the internet for all to see. So hopefully that explains everything you need to do. And anything else, just give me a holler. Love you. Bye.